Okay, questions? Evan. So you're asking about number 11. So the first thing I'm going to do is check to see if I can factor this. And now to find the domain, I'm going to take the denominator and set it equal to 0 and solve. So I get 2 here. For this piece, this doesn't factor, so I'd use the quadratic formula, but I find that I get an imaginary solution, so it doesn't matter anyways. So my domain is all real numbers except for 2. Now I notice here that this reduces to this. So this part that I've reduced away gives me a removable discontinuity at x equals 2. And when I plug that in to my reduced function, I can get the y coordinate for that discontinuity. So I have 4 on top and 12 on bottom. So that's 1/3. And since there's the denominator here, when I set it equal to 0 and solve, again, I get an imaginary solution, so there's no vertical asymptote. There's just that. The x-intercept comes from setting the reduced numerator equal to 0. So there's my x-intercept. And then the end behavior comes from comparing the degrees. So I notice the degree of the numerator is 2, which is less than the degree of the denominator, which is 3. So I have y equals 0 or y approaches 0. But since I do have an x-intercept, I know it's just going to be the approaches. Homer? Something like this, where the graph never crosses, is y equals 0. Something like this, where the graph crosses, is y approaches. Ferris? It was all real numbers except for 2. Next question. Ferris? Okay, how did you try to do this, Ferris?
Well, I was because I thought you said to multiply, but I was
Can't do that because it's not a proportion.
I was just trying to do something
Makes it not a proportion. So if you are stuck on trying to cross multiply, which I would not recommend doing, you'd have to combine these by making a common denominator, doing the subtraction. but that's going to be worse than if you don't do it that way. What I would do is I would try to make a common denominator throughout the whole thing or clear fractions. So if I make a common denominator out of the whole thing, my least common denominator would be x times x plus 3. So this first piece needs n, x plus 3. This piece needs both of them. And this piece needs okay to there, Ferris? Now, since the denominators are the same on both sides, you can forget about them. And I'm left with a quadratic equation. So if I move everything onto one side, I'm going to have 0 left on this side, 2x squared plus 3x minus 15. And I could try to factor that or use the quadratic formula. For the sake of argument, let's use the quadratic formula. So negative b plus or minus b squared minus 4ac. Make sure you take the negative sign along with that 15 over 2a. So we have 9, and then let's see, 60, so plus 120. So x equals negative 3 plus or minus the square root of 129 over 4. And then we should check to see if we can reduce the square root of 129. 129 does have a factor of 3 in it. That's 3 and 63. That has a factor of 3, oh, not 3 and 63, 3 and 43, right? Yes. And that can't do any more reducing, so that's our final answer. And obviously neither one of those guys give you a 0 denominator, so that we would accept both the plus and the minus.
So if there's like an add or subtract, like portion on one side.
If you have more than one fraction on either side, you can't cross multiply. That's an only, cross multiply only works for proportions. Only for proportions. Who's next? So this one could be really awful or not that bad depending on the order in which you do things. So I'm going to start by factoring everything. And if you screw up some of the factoring, you'll also find that you'll make this problem much harder than it needs to be, or than it should be. So just going through and factoring these things. And I see a couple of good things have happened right away. Okay to there? Okay, I'm going to distribute this now to both of these two fractions, because I noticed that when I multiply to this first piece, the x plus 3's and the x plus 2's would cancel. So when I do that, I'll have just the x minus 4 over the x minus 3. And when I multiply to this one, the x minus 3's will cancel, and the x minus 4's would cancel. So I'm left with just the x plus 3 over the x plus 2. And now I can just make a common denominator from here. Hopefully it's clear that that would just be x plus 2 times x minus 3. So I'd have x squared minus 2x minus 8 minus x squared minus 9 all over x minus 3 times x plus 2. And when I combine my like terms, I have negative 2x minus, distribute that through, so that's plus 9. So plus 1 over x minus 3, x plus 2. Yeah, had you tried to add the fractions first, it would have been really a lot more difficult way of doing it. So again, it's one of those like, you know that you can either do the stuff in the parentheses first, or you can distribute. Should look at what you have going on there, and by distributing first, you should have hopefully noticed, hey, if I distribute first, lots of stuff is going to cancel, and that makes life typically going to make life a lot easier for you. Gracie? Oh, there's a bunch of restrictions for this one too, right, guys? I guess we should have listed those. Let's see, what did we cancel? We should have a negative 1 from here, a positive 2 from here, a positive 3 from, oh, no, because it still stayed to here. So probably just those two, negative 1 and 2. Negative 3, yes. And then positive 4 also, sorry. But the positive 3 stays, and the positive 2 stays. So those ones we keep. Those ones are not restrictions because they make it to the next step. But the other ones don't. Okay, sorry about that. Gracie asked about the restrictions on 1, and I'm like, oh, we didn't do the restrictions for this other one, huh? So I'll start by taking a 2 out of the numerator and a 6 out of the denominator. This is a difference of cubes, so I know that factors. So those parts cancel, those parts cancel. So I have x minus 1 over 3. And then to find the restrictions, I'm going to set this piece equal to 0 and solve. That doesn't factor, so I'd have to use the quadratic formula. When I do that, I get imaginary things, so there's no restrictions here. Because we don't care about the imaginaries for restrictions. Only real numbers apply for restrictions. Are you okay with that, Gracie? And again, I skipped doing the quadratic formula because I trust that you guys can either type it into your program or just do it by hand. Like it's not, at this point, I hope that we're comfortable doing that. In the interest of covering more questions, I'll skip some of those like things that are subroutines of things that we've already done a bunch of times. Ferris?
Yeah, I just have a question. For 14, 15, 16, are they exactly the same thing as the last 12?
Yeah, but you got to make a table and then graph it. Who else has something? Read. So I'll start by factoring this because I'm going to need to do it at points anyways. So I notice my domain is going to be all real numbers except for plus or minus 3 by setting the denominator equal to 0. Since none of this reduces, I have two vertical asymptotes at negative 3 and positive 3. Again, from setting the denominator equal to 0. I have x-intercepts at negative 2 and negative 1. That's from setting the numerator equal to 0. And then my end behavior, since the degrees are the same, I know it's going to be either y approaches the leading coefficient over the leading coefficient, or y equals the leading coefficient over the leading coefficient. I'm not going to know which one it is quite yet until I look at the graph and I plot some points for this, though. This is the one where it's tough to tell the difference. Okay so far, Reed? Okay. So let's make our table. So 3 points, vertical asymptote. 3 points, vertical asymptote. And then 3 points. So hopefully those ones at the ends are obvious x's to pick. And in the middle, we got those guys. I might actually do 4 in here. I might do negative 2, negative 1, then 1 and 2. So I just built a fourth one in here just so I'd have a, I should probably have something in between those two x-intercepts, huh? Well, we just may pick up, oh boy, that was not what I wanted to delete. Sorry about that. We're going to have a lot of stuff in here, huh? So negative 2, negative 1. I need something in between there. So we'll have negative 1.5 and something. And then we'll do 1 and 2 or something like that. I don't know. It's going to be kind of a mess in the middle there, but it's okay. With me so far, Reed? Yes? Because they're both x-intercepts. I want, like if I do that, here's my x-axis, here's one x-intercept, here's the other. I don't know if I'm doing this, and then I do this, but like I don't know, do I do this, do I do that? And really I probably need something in between here also, so I know what it's happening, but let's plot these at least and then kind of see what's going on. This was just kind of a tricky little bugger, I think, because of the values, or what I picked as the numerator. I should have picked something that was a bit more spaced out. But it is what it is. It's not the end of the world. I don't know what you mean by that. Let's wait for a minute, okay? Let's get this part done, and then we'll come back and cover the what-if questions, okay? I'd be happy to address it, but we're in the middle of this, and I don't want to get down like a what-if rabbit hole. You know what I mean, guys? So let's just clear this out of here, and then we'll get that. Okay, so I have 0.74, 0.75, 0.86. And then we have 0, 0, negative 0.22, negative 0.75, negative 0.24. That was negative, wasn't it? Okay. And then we have 4.3, 2.6, 2.1. why I put a 7 there. I don't care about the 7. Let's go back and get that. Negative 1.5. I forgot about him. I'm just going to do it this way because it's a little bit quicker. So that's 0.4. All right. And let's take a look at what this looks like if we go and plot these points now. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. These are all so small except for this one. I'm just going to... Oh, these ones are pretty big too. Jeepers creepers. I guess I'll go up by ones. It's pretty dumb to do it that way, but... it's kind of the bed that I've made for myself in drawing this rather small. So those are my asymptotes. And I have let's see. There's something here and here and here. That's really weird. I'm going to probably add some more points in there in a minute. So I have this. I have that. I have this. I have that. Oops. I have that. And then I have like that. So this to me looks like it's going to do something like that in there. And then this one looks okay with what's going on here, that it's just like going to be that. Let's go back here though and get some more stuff in there. I want some things that are closer to this asymptote. Like I can see this stuff is going to just be kind of following, but I want to know what's going on kind of over here still. So I'm going to go back and get like, pull out like negative 4, oops, like negative 3.5 and something, just so I can see what's going on with that. So again, you can do the change your step to include halves. I'm just going to do it this way. Okay, so 1.5. So if I do that, that's up here now, so it looks like I must be coming in kind of like that. And now Palmer, 1 second. What is this? Is this the asymptote or the approaches? This problem, right? We said we didn't know. We said it was going to be either this one or this one. Good. Why? Yeah, because we have this spot right there where it's crossing. Katie? Leading coefficient over leading coefficient. Since the degrees were equal, it's leading coefficient over the leading coefficient. So 1 over 1. We have to do it all the way through. Is that okay, Katie?
Is that horizontal line on 1?
Yeah. This is the y approaches 1.
So that's the end of the series?
Kevin? So like 15? So we have y equals x cubed plus x squared minus 4x, minus 4 over x squared minus 1. So I'll start by factoring this. I'm going to factor the numerator by grouping. So I'm going to shortcut in the interest of time all the way through to the factor by grouping answer. Are you okay with that, Kevin? Okay. So my domain is all real numbers except for plus or minus 1. My discontinuities, well, I notice that I can do a reducing here. So I have a removable discontinuity at x equals negative 1. And when I plug negative 1 back in up here, I have negative 3 times 1 over negative 2. So that is, that's not the thing I wanted. I wanted this. So negative 1.5. Oops. Positive though, right? Yeah. And I also have a vertical asymptote at x equals positive 1. You good with that? Okay. I have x-intercepts at negative 2, 0 and positive 2, 0. And my end behavior is going to be a slant asymptote. So the part that I'm going to use to find the slant asymptote is going to be this part. But to do that, I'm going to have to FOIL that numerator back out. So what I really have is x squared minus 4 over x minus 1. Okay? So x minus 1 is on the outside. X squared plus 0x minus 4 is on the under. And then I'll ask myself, what times x gives me x squared? Well, that's x. I distribute that to both pieces. So I get x squared minus x, and then subtract down. X squared minus x is 0. 0 minus a negative x is positive x, and I'll bring the minus 4 down. So 1 times x gives me x. So I distribute that over, and then subtract down. So my slant asymptote then is y equals x plus 1. So it's just the quotient from this polynomial division. Are you okay with that, Kevin? Are you sure? You mean negative 3? Sure. You're right, but it doesn't really matter because the remainder doesn't do nothing. But yes, thank you for catching that. Yeah, Katie?
How did you get the removable discontinuity 1.5?
I plugged negative 1 into the reduced part up there.
The reduced part?
Yeah, the highlighted in green. Because if I plug negative 1 before I did the reducing, I just get undefined. Right? Mackenzie?
How did you know that it was a slant asymptote?
Degree of the numerator is bigger than the degree of the denominator. Correct. So 1, 2, 3, and then my vertical asymptote is at 1, right? Yeah. So there's that. Oops. Good to there. Okay. And so I'll just fill in those values. I'll use the calculator to do it. What am I going to type in, though? I'm going to type in the reduced version. X minus 1. So 0 is 4, 3 is 2.5, and 4 is 4. So what was it again? 4, 2.54. I need a second XY table, though, for this, because I also need one for my slant asymptote. So I'll just pick some values for x. Let's say I pick 0 for x, and I get 1 for y. And let's say I pick -1 for x, and I get 0 for y. So I got this in here, and I got this in here, and then I have this, this. So we're going to come in and do like one of those. Oops, what did I forget to do though? That should have been open. Why is that open? It's the removable discontinuity. So this one's going to do like one of that. Oh my God. So open. That's what I mean by open. Yep. Kevin, you feel okay with that? So again, just remembering how to do that polynomial division from last semester, but they're usually not really long ones. They're usually like 1 or 2 steps like that. So hopefully not so bad. Who else? Going once. Going twice. Okay, I'm all